Okay, good evening, good afternoon, everybody, wherever you are. Today we have Professor Jorge Piekarewicz from Florida State University. Most of you already know him and his work, and this is what he is going to take us through today, which is basically understanding nuclear matter properties at extreme conditions, looking at the perspective from both from heaven and earth, and that is what his title says. And if you don't have any pressing question, you should hold on to your question until end. But if you have really something really pressing, you can just unmute yourself or raise your hand, and you can ask the question right away. But we'll also appreciate if you put the question in chat and things can go on there as well between yourselves. Even Jorge doesn't need to know everything. And at the end of the talk, we have some informal gathering with him in a different space. I think Anna has already put the link in the chat box. We'll do that again while the talk is going on. So see you there after the talk. If you have something informal, if you do not want to ask during the talk. So without further ado, Jorge, please.
Thank you so much, Chiranjeev. That's a very kind introduction, and thank you also, Anna, for inviting me. I think this seems like a very nice space to share some of the results. And basically, according to my instructions, what I will try to do is just give you a perspective, and of course, it's a very personal perspective of some of the latest developments that we have seen in the field. And then just to set the stage, let me just, as you all know, start with a truly gift from the heavens, which was GW 170817. So as you all remember, this was the first time that we were able to detect gravitational waves directly from the binary merger of neutron stars. But of course, this is also a multi-messenger event in the sense that I will play in this video. Then not only did we be able to detect gravitational waves, we saw a short gamma ray burst, and then of course at the end what remained was a kilonova. So let me just start by setting the stage by playing this video that many of you may have seen. So when you have these two neutron stars and they're well separated, it's basically indistinguishable from two-point black holes, two-point particles to black holes. But as they get close to each other, then they start to distort. They emit gravitational waves. And then 2 seconds later, then you see this back-to-back jet. That's what we call the short gamma ray burst, which until then, we were not completely sure that it was actually associated with neutron star mergers. And then, of course, this little thing that is left behind is the kilonova, which we believe, or at least some people believe, is being powered by the radioactive decay of our process elements. So in one single event, I mean, essentially we learn an amazing amount of physics that we're still trying to understand to this day. This is an even cuter type of video in which first you see the LIGO signal, and then at time from merger cert, you see the chirp, and 2 seconds later, you have the short gamma ray burst, which actually was detected by the Fermi telescope. So it was truly a memorable event, even science, namely the breakthrough of the year. So this is by normal cartoon of a neutron star. It was not, it was not given by me. This is a very nice picture that Danny Page at UNAM actually crafted that I've been using for many, many years. And unfortunately, I won't be able to tell you everything about every single layer in the neutron star. The neutron star is extraordinarily interesting. It's far from just a big nucleus with a collection of neutrons. But if there is time at the end, and if people want to understand some of the different layers and the rich physics in each of these layers, I will come back. So most of my talk will be concentrated in what we call uniform neutron-rich matter. It's where most of the matter is contained, and it's approximately 10 kilometers of the size of a star, which is typically, let's say, 12 to 13 kilometers, is concentrated in that region. So why are neutron stars so fascinating and so relevant to nuclear physics? So the first thing that I'm just going to tell you, as you know, I mean, neutron stars are the remnants of massive stellar explosions called collapsed supernova. And then to try to understand their properties, we solve what's called the Tolman-Oppenheimer-Volkoff equation, which is basically the equations of hydrostatic equilibrium, but then you extend Newtonian gravity to Einstein gravity. And they are encoded basically in these equations over here. Now, what is interesting is that these equations, in order to solve them, I mean, they're not particularly different to solve, but what you will need is a connection in order to be able to solve them between the pressure support that is preventing the gravitational collapse of the star and the energy density. And this connection, of course, it's an input that, let's say, the user has to provide, and that's the equation of state. So the equation of state is essentially the most important unknown in the equations of hydrostatic equilibrium. And one of the things that is particularly interesting for our field is that if you look at other compact objects, in the particular case of a white dwarf star, if you actually simulate the equation of state by simply assuming that the pressure support is provided by the general electron gas, then basically you describe the structure of a white dwarf star. And that is actually the first calculation that was done. It was done by Oppenheimer and Volkoff, and they say in the same way that electrons support a white dwarf against gravitational collapse, let us assume that a neutron star is supported by the degeneracy pressure from the neutrons. And that is a calculation that they did in the 1930s, and they came with a very interesting result that you can have up to 0.7 solar masses of neutron stars. Above that limit, then the neutron star essentially will collapse into a black hole. But of course, we all know that, and at the time that I did this slide, or I borrowed this slide, we already had at least one neutron star with a mass of 2 solar masses. So clearly the pressure support for the neutrons is not sufficient, and not something else has to provide the additional support to be able to go from 0.7 up all the way to 2 solar masses. And of course, this is high density matter, so it's the nuclear interactions at short distances that becomes very repulsive, and it's responsible for essentially going from the Oppenheimer-Volkoff limit to the limit of at least 2 solar masses. So that basically was the status before GW170817. And one of the things that I want to bring to your attention is that, of course, everyone that you see in this plot is solving exactly the same TOV equations. The only difference is the input for the equation of state. And this essentially encapsulates how little we know at the time about the equation of state, because you were able to say that, for example, for a canonical 1.4 solar mass, then depending on your model, then the radius of such a star can range all the way from essentially 8 kilometers all the way to 15 kilometers. And it's interesting because many of these actually are nuclear models that account for the properties of finite nuclei. But yet, when you extrapolate to high density, of course, that extrapolation is largely uncontrolled. And then you get this very, very large spread in the predictions for the radius of a neutron star. So given that the equation of state is the absolutely essential ingredient to understand neutron stars, just to remind some of the students in the audience about some textbook examples of the equation of state. So if you have a very hot object, let's say, that you can treat classically, and by classically, I mean that you are in the regime of temperature and density, such that it's very high temperature and it's low density, then you can approximate the equation of state as that of the ideal gas. So you have the pressure, which is an intensive quantity, and then it depends on 2 intensive quantities. One is the number density, the other is the temperature. And this, of course, is the equation that we learn in I don't know, maybe high school, maybe a little bit later, which is just pressure equals NKT. Now, if you go to the other extreme, like for example, that you need to describe white dwarf stars, then in that limit, you assume that actually you are in a quantum gas limit in which the density is very large, and then the proxy for the high density, namely the Fermi temperature, is much, much larger than the actual temperature of the system. In that case, you can treat the temperature effectively as 0, and then you just have one intensive quantity in terms of the density. And then for an ultra-relativistic gas, it scales like the 4/3 powers of the density. If it's non-relativistic, it's just 5/3. Then, of course, now you go away from the textbook examples, and then you try to describe nuclear physics. So nuclear physics, of course, neutrons and protons can be described as a strongly interacting quantum fluid. And again, you are in the regime in which you're a high density at low temperature. So everything that I'm going to say as far as the neutron star is concerned is going to be assuming that the temperature is equal to 0, not because the temperature is 0, but because the Fermi temperature is much, much larger than the temperature of the system. Of course, we have two quantum liquids, and they are in chemical equilibrium. Then, of course, one of these quantum liquids is charged, namely the protons. So you have a macroscopic system, so you have to impose charge neutrality. For that, you have neutralizing leptons, mostly electrons. But of course, because the density is so large, then at one point it becomes energetically favorable to start populating the leptonic sector also with muons. And then finally, we want to get some insight into both the density dependence and the isospin asymmetry of the equation of state. And those, of course, are poorly constrained because our information from nuclear data is basically systems that are very, very close to symmetric. Of course, FRIB is going to change that with a completely new paradigm. And again, the density that we probe is mostly densities that are around saturation density. So one thing about the equation of state that many people in the audience make a living of trying to understand better is the symmetry energy. So let me take you through this cartoon very quickly. So if you have symmetric nuclear matter, and then you try to compute the equation of state, namely the energy per particle as a function of the density of the system, then you get a characteristic curve that looks like this. And then one of the important points, of course, is that there is a minimum in the equation of state, namely that the minimum means that, of course, the energy with respect to the density for a t equals 0 system means that you're talking about the pressure. So at this point, the pressure of the system vanishes. And then we're trying to understand what happens to the system as we go to higher densities. So what I like to say is that in this case, you have what we call a symmetric bucket. And imagine that you have a container such that the number of particles in the system and the volume are such that the density is about 0.15 nucleons per Fermi cube. So in that situation, if you have a piston, then the piston will not push on the system, and neither the system will be pushing on the piston, because of course the pressure is equal to 0. But that's very different if you start now trading, for example, protons from neutrons. So now, of course, because you have the Pauli exclusion principle, if I want to move protons from here, I have to go above the Fermi surface, and that is going to generate a pressure which is different from 0, and that pressure we quantify through the symmetry energy. So the symmetry energy basically, to a very good approximation, is just the difference between the energy per particle of a system, which is made exclusively out of neutrons, relative to this system at exactly the same density, but one in which neutrons and protons are equally divided. So that is the symmetry energy, and that's a quantity that some people call AV or SV, and here in this talk I call it J. But more importantly for this discussion is what is the pressure that is being generated at this particular density. And that is a quantity that normally people call L. And again, because nuclear matter saturates, this quantity L is essentially to a very good approximation, very closely related to the pressure of pure neutron matter at saturation density. So every time I talk about L, you can think about a system that is made exclusively out of neutrons at saturation density, namely again, 0.15 nucleons per Fermi cube. And then you can think about either L, or you can think about just the pressure of a system made exclusively out of neutrons. And then if L is very large, then we say that the equation of state is stiff. and if L is relatively small, then we call it that it's soft. So that's the 3-minute tutorial on the equation of state. So again, I don't want you to read everything in here, but I gave you essentially the perspective on the field before GW 170817. Since then, many things have happened, and not only within the realm of gravitational wave detections. There have been more. Certainly the gold-plated is still GW 170817. But on top of that, we have seen many other developments with electromagnetic observations that I'm going to discuss. And of course, also with terrestrial experiments. So this is basically some of the things that I will be covering. And the way that I like to organize these is to paraphrase some of our colleagues in cosmology that want to use different tools to actually calibrate the distance to the object, right? So distances are very hard to measure in astronomy. So they have this cosmic distance ladder in which you use, for example, radars, and then you use parallax and other approaches to go from objects that are very close to the observer to objects that are much farther away. And in the same way, I like to create the nuclear equation of state ladder, that it starts with experiment in the laboratory to constrain the density in the range of nuclear matter saturation density. And then if you go a little bit higher, then you can use heavy ion collisions. So many of our colleagues use heavy ion collisions precisely to try to understand the equation of state of dense matter in a region where it's highly asymmetric, much more neutrons than protons. And here you also have, for example, NICER, which I will talk. And then the next rung in the ladder, then you say, okay, let me find the region of overlap between gravitational waves and essentially the NICER physics. And then finally, gravitational wave with pulsar timing, which gives you very accurate description of the masses, which is basically neutron star masses is what constrains the equation of state at the highest density. So this is the nuclear equation of state. And now let me describe some things starting at the higher densities, which in some ways is chronologically what happened. And then I'm going to go down until I get to the laboratory. So how do we measure heavy neutron stars? So there is a very interesting technique, which is completely based on general relativity. So you all remember from Newtonian gravity that if you know the semi-major axis and the period of the orbit, then you can constrain the sum of the masses of the two rotating objects. So for us, it's not very useful because what we want, if you have a neutron star orbiting a white dwarf, if you have this kind of binary system, we want to know separately the mass of the neutron star at the white dwarf because we want, of course, to place limit on the equation of state. So this doesn't help, but there is a correction to formulas like these that come from general relativity, and in particular, one that has been used very much by the observer is this thing called Shapiro delay. So Shapiro delay is a purely relativistic effect that can break the degeneracy that you have when you only can constrain the sum of the masses. And the idea is the following. So imagine that what you have is, again, a white dwarf and a neutron star. And imagine that the red object is the neutron star, the blue object is the white dwarf, and the observer is to the right. So the neutron star is emitting radiation, let's say magnetic dipole radiation. And when it passes through the gravitational field of the companion white dwarf, then it's going to dip a little into the gravitational field, and then it's going to go out. So basically, if you measure a delay in this kind of configuration, then you see a delay, which is typically of about 20 microseconds. If you are, however, in these kind of configurations, or even in this kind of configuration where the white dwarf is here, the neutron star is here, and the observer is here, you don't see any delay. So the nice thing about the Shapiro delay, again, is a purely gravitational relativistic effect, and essentially isolates the mass of the white dwarf because, of course, the time delay is due to the gravitational well of the white dwarf. And by doing this, you can separate them. So that is basically what people do. They do timing. So they sit for a long time. They achieve extraordinarily good statistics. And then a few years back, you probably heard that even CNN told us that the most massive neutron star ever detected is straining the limits of physics. I think straining the limits of physics is a little bit of a stretch, but it certainly was a very, very important observation. And then it came with a maximum mass of about 2.17 solar masses. So again, we are in this region. And then if you go from 2 to 2.2, let's say, then of course, what you need is an equation of state will be stiff enough that you will be able to reproduce this kind of mass because before your gravitational collapse into a black hole. And then you see that there were some equation of states. For example, we have one here at FSU that we calibrated before we knew about 2 solar masses. So we were completely agnostics, and then we recalibrated a functional. It came out with a value of about 1.7. And since then, we have information, and then basically you have stiffened the equation of state because now you have a very nice constraint on the maximum mass, which again, as I told you here, is constraining the equation of states at the highest possible densities. Okay, so then let me go and tell you why this event has been fantastic, GW170817. So encoded in the gravitational wave profile, so you see the gravitational wave profile, and then they are very useful information that can extract. And one of the information that is difficult to extract, but you can extract, is what's called the tidal deformability or the tidal polarizability of the star. So to explain what it is, I always want to go back to a textbook example. And this is not, of course, within the realm of gravitational theory, but it's mostly in electromagnetism. And we all know what the electric polarizability is, right? So for example, imagine that you have a polar molecule like water, and then you place that polar molecule between the plates of a parallel plate capacitor. You turn the plate, and then of course, the electric field, which is the external agent, is going to induce a response in the drop, namely a polarization. And if the electric field is not very large, then that response is going to be linear to the external stimulus produced by the parallel plate capacitors. This quantity chi completely characterizes the material, and of course is the electric susceptibility. So the same example can be applied when you have systems in gravity. So if you have 2 stars, then the tidal field of one of the stars will induce a mass polarization, if you want, of the star. And then again, so you have a tidal field, and that tidal field is going to induce a response in the star. It's going to develop a quadrupole. And again, if the tidal field is not very large, then you have a linear response. And the linear response is encoded in this quantity here, which is the tidal deformability of the star. And already GW170817 came with some results. This is actually directly a plot from the discovery paper. And then they tell you that less compact, more compact, that the analysis from this one event is actually favoring more compact stars. And they actually reported that if you have a neutron star of a mass of about 1.4 solar masses, the tidal deformability, which is it's essentially dimensionless quantity, has to be less than some number. And then we did some analysis within our models, and then came with a radius of about 13.76 kilometers. So we already placed some limits from the tidal deformability on the possible radius of a neutron star of a 1.4 solar mass. And again, I like to say that the tidal polarizability measures the fluffiness of a neutron star against deformation. And it's very, very sensitive to the stellar radius, which is one quantity that is notoriously difficult to compute or to measure. And you can see it here, this quantity actually scales like a quantity that is referred to as the love number. And then it's just the ratio of the radius of the star to the Schwarzschild radius, but it's raised to the 5th power. So we have a very nice lever arm in connecting lambda to the radius of a neutron star. Okay, so I told you about essentially how do you measure stars and then how you constrain radii by doing the tidal polarizability. let me get to the latest discoveries that we've done with the neutron star interior composition explorer. That's nicer. And it's the first time, even though the field of neutron star physics has been around for a long time. I mean, what is really historic about this mission is that it has provided for the first time simultaneous constraints on the mass and radius of two different sources. So I have them here, but let me tell you first what it is. It was very nice because, of course, as you probably know, it was actually launched aboard the SpaceX Falcon 9 rocket, which of course is Elon Musk's baby. It docked a few days later at the International Space Station, so that's where it is now. And since then, it has been performing a most detailed study of neutron stars. One of the things that is really, really interesting, and of course also has to do with the fact that you're talking with a very, very highly general relativistic object, is that there is the bending of the light. So one of the things that is very, very nice is that you can look at light that it's emitted from the back of the star. And the more of the light emitted from the back of the star you see, that it basically is telling you that the star is very, very compact. Namely that for a given mass, the radius is very small. So I mean, I have a cartoon that I actually stole from there. So this is what we call a hot spot in the star. And then basically what happens, even though it's not obvious here, is that when it goes to the back, that in principle you couldn't see it, then the pulse profile that they detect is still detecting photons from that hot spot, which essentially is constraining the compactness of the star. So I'm just going to play it for you. There is nothing particularly interesting other than you can see the back of the star. But then some of the results that we got, the first source that they measured that has this telephone number, J0030, has a mass in the what we call the canonical range of 1.44 solar masses and has a radius of about 13 kilometers. So unfortunately for this source, there was no previous measurement of the mass. So you only get the compactness. So then basically you don't have a measurement of the mass to determine the radius, so you determine them simultaneously. But this is the star that I showed you before. So this star is this star over here, the most massive star that we have. And they have just reported recently a measurement of the most massive star. And of course, in that case, you have the mass of the star because it was measured before by electromagnetic means. And then they put a limit of 13.7 kilometers, which is fairly large for the radius of this star. So a lot of fantastic developments in the past from electromagnetic and gravitational wave detections. Okay, so then the last part of the talk is trying to tell you where terrestrial experiments come into play. And one of the things that I mentioned at the very beginning is this quantity L that you can associate with the pressure of pure neutron matter at saturation density. Now, of course, these quantities are not physical observables. You cannot bring a chunk of neutron star and ask your experimental colleague to measure it. So you have to infer it. And then one of the things that we found out from the very beginning is that there is a very, very strong correlation between the quantity that you're after, namely a fundamental property of the equation of state, and then the neutron skin of a heavy nucleus. So here what I plot is you take your favorite model, and then you ask your colleagues for two quantities. You say, please compute the pressure of pure neutron matter in your model, and also please compute the neutron skin of lead-208. So the neutron skin is nothing more than the difference in the radius of the distribution of neutrons relative to protons. So if you look at lead, lead has 82 protons, and then it has 126 neutrons. So in a very simplish, cartoonish way, you can imagine that protons and neutrons, 82 of them, are making the core. And then there is a dilute region that is outside, which makes essentially the neutron excess. And then the difference in the red ball relative to the blue ball That's what we call the neutron scheme. So then your friends give you the L, your friends give you these, you put them on a plot, and then you find out that regardless of the models that you've used, and again, let me clarify, these for the most part are density functional models, you got an extraordinarily strong correlation. So then you say, okay, so that's fantastic. I want a fundamental property of the equation of state that is going to constrain properties of neutron star. I'm going to go to the lab and do a measurement of the neutron scheme. So again, in another a little bit more intuitive way, if I have a model, then I'm going to calculate the distribution of protons in lead. I'm going to calculate the distribution of neutrons, and then I'm going to look at the root mean square radius for each one of them, and this is going to give you the scheme. But one of the things that is really, really interesting is that whereas the pressure of pure neutron matter in the case of the nucleus is pushing against surface tension, is precisely that same pressure that's going to push against gravity in a neutron star. So then you do similar correlation plot for two different masses. One mass is one neutron star has only an 8/10 of a solar mass. The other one is the canonical 1.4 value. And then you see that there is also a very strong correlation. So that tells you that whether you're pushing against surface tension in a nucleus or you pushing against gravity in a neutron star, this L is the proxy for both. So you're essentially connecting a quantity that you measure in the lab to a quantity that you measure by observation that differ in 18 orders of magnitude, but essentially have the same source of pressure support. So I'm going to talk a little bit about the campaign that just finished for the PRex II. They reported some results. And then the future is away from the US now. Jefferson Lab will no longer continue to make that kind of experiments. There is new facility at Mines that is being built. It's called MESA. And then the hope is that our colleagues there will take the baton and then try to make more precise measurements of the neutron scheme. So I told you how our observational friends constrain properties of neutron stars either by pulsar timing, pulse profile in the case of NICER, gravitational wave. So let me tell you how our experimental colleagues at Jefferson Lab were able to determine the neutron scheme. So what is the physics behind that? Well, so of course, we knew about the charge density from very, very long time ago. So in the 1950s, Hofstadter at its flag measured the charge distribution of many, many nuclei with very high precision. He went on to get the Nobel Prize. So that, of course, we do via parity conserving elastic electron scattering. If you have an electron, the electron is going to emit a photon. Photons like to couple to charge, so they're going to couple to the protons in the nucleus, and they're going to give you a very accurate distribution of the charge in the system. But of course, photons do not couple, at least at q square equals 0, they do not couple to neutrons. So then basically all that information that we've got about the neutron distribution, we obtain with hadronic probes, let's say pions, protons, and so on. But there is another way of doing it in a much cleaner way, namely using only electroweak probes. And that you can do by also emitting an electron, so also having an electron, but in this case, instead of emitting the neutral quanta of electrodynamics, you emit the neutral quanta of the weak interaction, which is the Z0 boson. And in the same way that particles in the standard model have electric charge, they also have weak charge. And it turns out that the weak charge, the weak vector charge of particles is given by twice the weak isospin minus 4 times the electric charge times the sine square of the Weinberg angle that characterizes essentially the mixing between electromagnetism and the weak interaction. Turns out that sine square of theta W is very close to 1/4. So you can approximate and say it's just twice the weak isospin minus the charge. So the interesting accident is that for the coupling of a photon, of course, we already saw that the neutron vanishes and the proton gets 1. For the Z0 coupling is almost the opposite. So the weak charge of a proton is very, very small and it's very large for the neutron. So what you can do is essentially an interference experiment in which you calculate the asymmetry, the parity violating asymmetry which is nothing more than cross-sections for right-handed polarized electrons relative to left. You get some fundamental parameters of the equation of the standard model. And then you get the ratio of two quantities, the form factor, which is the Fourier transform of the charge density, or the weak density. So the form factor is just the Fourier transform. So the weak form factor, which essentially is related to the neutrons, because essentially the protons don't contribute, and the charge form factor, which is mostly the protons. We know the charge form factor, so that's a very good way to extract the weak form factor of the nucleus. So it's also very nice because these electroweak experiments, which I will, as you probably know, there are two of them at Jefferson Lab, will also provide fundamental anchors for future campaigns at FRIP, or other exotic beam facilities. Of course, in that case, you have hadronic probes. So you have hadronic corrections or hadronic uncertainties from the fact that the probe is hadronic, but at least you will have two very nice anchors from JLab experiments to calibrate. So this is very, very quick. I don't want to tell you a lot, but there are, of course, a lot of connections. So here's the connection between what measuring neutron skins and then the connection with FRIP. Turns out that exactly the same weak form factor that you measure in parity violating electron scattering, you also measuring in coherent electron, neutrino, neutron scattering. So there are many, many, many kinds of relations. And of course, one of the things that I will not have time to talk about, there is also complementarity with other observables. And some people at Michigan State University have been very involved in trying to constrain the slope of the symmetry energy by looking at charge radii of mirror nuclei. And of course, the beauty of that is that charge radii, we in principle know how to measure, although these, of course, experiments involve some unstable nuclei. But what I'm trying to tell you is that there are many electroweak options to constrain the weak distribution of a nucleus. So now I'm going to show you some results. I don't want to go through a big spiel about what density functional theory is. All that I want to tell you is that Walter Kohn, who of course is a physicist, won the chemistry Nobel Prize for the development of density functional theory. One of the most important theorems of this is that you construct a functional. So it's not a wave function that depends on many, many, many coordinates. It's a functional that depends on the energy of the system. And then he proved that you can get the exact ground state of the system and the corresponding ground state density from functional minimization. Now, why did he get the Nobel Prize in chemistry, not physics? Well, chemists know the interaction, nuclear physicists don't. But we have been trying to apply covariant density functional theory or non-covariant density functional theory. And here I very succinctly tell you what the aim is. The aim is to build a high quality functional that yields an accurate description of the properties of finite nuclei, namely ground state properties and collective excitations, but also generates an equation of state that is consistent with known neutron star properties while providing a Lorentz covariant extrapolation to dense matter. So one of the things that we already know, because the density in neutron stars can be very large, because we already know that we have neutron stars with at least 2 solar masses, is that if you don't have a Lorentz covariant extrapolation, one of the things that happen is that your equation of state becomes acausal, namely that the speed of sound can exceed the speed of light at the very highest densities. But I don't want to say anything more unless there are questions. This is the framework in which I'm going to present the calculations. Okay, so what happens with PRex and PRex II? The announcement was made almost a year to the date. It was made in the 2020 DNP meeting. And basically in this context, what we have is, so PRex was run some time ago. The error bars were relatively large. PRex II reduced the error bars by about a factor of 3. When you combine the result, then you get a neutron skin that is relatively large, 0.29, with an error bar of about 0.07 Fermis. So the error is still a little bit large, and that's what I mentioned, that the future of these kinds of experiments, at least in the electroweak sector, will be done at mines. But one of the things that was already interesting is that people have used in the past some hadronic reactions to try to get at the same number. So for example, here there is coherent pi-0 photoproduction, antiprotons, and so on. And one of the things that I want to illustrate with these points is, number one, how easy it is to underestimate the systematic errors, not necessarily statistical errors in the experiment. It's the systematic errors that you obtain when you use these strongly interacting probes. So again, you could have said there was a tendency in the community to say, we already know the results because we have this very accurate value of coherent pi-0. So what is the need of doing the PRex experiment? So for me, the need is that you have an electroweak experiment that gave you this value, where there is something that is contaminated by hadronic corrections, suggested something very different. At the same time, there were already predictions from different sectors. Again, most of the predictions seem to suggest that the equation of states are relatively softer than indicated by PRex and PRex II. Here are some of the values. You see that this is for the quantity J. Most of them fall to the left. This is for the quantity L, and these are also some of them falling to the left. So, this is a slide that I stole from Christian Rischler. He was kind enough to share it with me. And then he had this in his paper, and then essentially we just added some of the constraints from PRex II. So the idea is that PRex II seems to want an equation of state, at least in the vicinity of saturation density, that is relatively stiff. Okay, so now you put everything together, and then this was the picture that we had prior to GW170817. I showed you this before. And then honestly, you can say that the most significant constraint that we had at this time was this constraint from the 2 solar mass that we obtained some time ago. And again, the constraint is, of course, in the vertical direction. If your equation of state cannot reproduce a 2 solar mass neutron star, then your equation of state is not stiff enough, so you have to do something. There was essentially no constraint in the horizontal direction. But now you can see that these constraints are coming now from, it is theoretical analysis of GW170817. So these are constraints coming from gravitational waves. You can see here constraints coming from NICER. There are 2 groups. So then you get something that, of course, they overlap, but it's not the same result. And then here's the NICER result for the most massive star. So lots of constraints are coming into play. And of course, in the middle panel, what I try to show is how do you put essentially a quantity that you measure in the laboratory. This is the skin. Remember the PRex II value is around 0.28. And then the hope, and this is a realistic reduction in the error bars if you can go to MREX at Mainz. And then here is the tidal deformability of a 1.4 solar mass neutron star, and this is the corresponding radius. And everything seems fine. So you get a region where things seems to be okay. There is only discrepancy in here. So let me just mention this quantity here, because for me, it still remains a little bit of an open question. The discovery paper from LIGO gave you this 800 number that I've already mentioned before. There was a revised upper bound that came in much, much, much lower. It's very hard, at least with the kind of models that we have, to try to reproduce such a soft equation of state. I've heard from some colleagues that not everyone trusts in the second analysis, but since I don't understand the analysis, I'm not going to comment any further. So this might be an interesting glitch in here that we do not understand. But if you remove some of these, LIGO still favors a relatively soft symmetry energy. So of course, we've been advertising this tantalizing possibility for a while. Given PRex, these laboratory experiments seem to suggest large neutron radii for lead, which essentially is telling you that the equation of states is relatively stiff, at least in the region close to saturation density. On the other hand, gravitational waves suggest small stellar radii. This is the region that they sample more or less. However, this has been mitigated a little bit because NICER, you can see that NICER actually allows for a little bit larger radii. So this maybe is not mitigated, maybe not. This remains an open question. But of course, ultimately, the equation of state needs to stiffen again because you have to reproduce two solar mass neutron stars. So this back and forth between stiff, soft, and stiff, if this doesn't get resolved, may be some kind of tension in favor of some kind of equation of state or phase transition happening in the star. Okay, so I think that at this point I was a happy camper. I thought things were coming together, and then we have to analyze a little bit more. And then at the beginning of this month, the DNP happened, and we got the results from CRex. And let me tell you a story that most of people in the audience may know. So this is Isidoro Isaac Rabi, a very, very famous physicist that worked in Colombia. And it's been said that when Rabi heard about Anderson discovering the muon, which for all intents and purposes is a particle that is identical in all respects to the electron, except for being 200 times heavier, he actually said, who ordered that? And to tell you the truth, that's exactly what I had in mind when I saw the results from the CRex collaboration. So the results from the CRex collaboration that are in here actually seem to suggest a very thin neutron skin in calcium-48. So of course, I was under the impression that the PRex result was going to come up with a large value for the skin in calcium-48. So after PRex II, the first thing that I did is I said, given the kind of functionals that we have, and given the result for the neutron skin in lead, what are the predictions that I'm going to make for the neutron skin in calcium-48, nickel-68, and tin-132? And you can see that this is calcium-48. Everything to the right, namely the thing that has under the yellow panel is allowed, things to the left are not. So in my book, given PRex II and given the functions that we had, I said there is no way that CRex is going to come with a value for the neutron skin that is less than about 0.21. Well, what they showed, the collaboration, and then this was given by Karin Palacci, she gave the collaboration talk at the NP. So she actually reported what it's called the weak skin. So it's not the neutron skin, but you fold in essentially form factors. And she make a plot for different values of the weak skin. And the phi variable number is 0.15. And then you say, well, if this is the correct number, what does that imply for the skin? And the value is extraordinarily small. In fact, in my plot, I don't even have 0.10. So what is happening? I don't know. Let me just conclude this by telling you what Karen said in her presentation. She says CRex result is consistent with a thin neutron skin prediction. For example, we do have one from coupled cluster calculations that predict a relatively thin skin in calcium-48, and is strongly inconsistent with predictions of a very thick skin. At this point, it appears potentially challenging for DFT models to reproduce both the CRex result of a thin skin in calcium and the PRex result of a relatively thick skin in lead-208. And what I add in here is that, to my knowledge, there is no single theoretical model that can reproduce both the very thin skin in calcium and the very large skin in lead-208. So let me conclude. I thank you very much for your attention. One of the things that I wanted to impress upon you is, of course, the progress that we have been doing in the field as a whole, this very beautiful synergy between many, many, many different fields. It's all connected, and it will remain connected if we want to understand dense matter. Multi-messenger astronomy is here to stay, and the nuclear community will play a very important role. These are some of my collaborators and some of the students that I had the pleasure to supervise that had actually a role in some of the things that I described. These I call the new generation, but as 2 days ago, all of these have already obtained their PhD. So these are my academic children. Brendan Reed is someone that I've been working a lot. So he's not my academic child, but it's like a stepchild that we have been working together. So I want to recognize his effort. And with that, I would like to conclude. So thank you very much.
Thank you so much. It was so wonderfully presented.
Thank you very much.
So the session is now open for questions.
Do we just speak up? Or should I raised my hand, but
yeah, I see Dr. Lynch has raised his hand. Please go ahead.
yeah. So Jorge, I mean, I'm going to go way back in time, but we had this meeting in 2014. At that meeting, we discussed CRex, and I recall your comment about CRex being a more model-dependent quantity to calculate. And I can't remember whether that was coming from the fact that the shell is not as strongly closed as lead-208, or was it some other reason? Can you explain?
Yeah, so thank you so much. I mean, that's a very, very useful thing. So clearly calcium-48 is it's not, for trying to understand bulk properties, is definitely not as good as lead-208. But then given that nature only provides us with two doubly magic nuclei, with like calcium-48 that are neutron-rich and lead-208, then of course calcium-48 was a very, very good alternative to lead. The real reason that also calcium-48 was selected is because we had a JLab workshop in which coupled cluster calculations already suggested that they can calculate from ab initio properties of calcium-48. So we presented as one of the motivating factors the fact that you have density functional theory, you will have ab initio, and then ab initio might build a bridge that we can tag into and learn something about ab initio calculation for density functional theory. So what you're saying is absolutely true. For bulk properties, calcium-48, it's a more, it's not a good nucleus, but the idea was, can we learn from ab initio? And of course, that's the hope, right? I mean, coupled cluster was able to reproduce, we haven't. So are there some important correlations that we are missing that with this conversation with ab initio, we will be able to have? And then one of the things that actually gives me pause in trying to understand how good calcium-48 is that clearly there are correlations in calcium-48, and I'm going to mention just one, that are way beyond the density functional theory. And here is the level scheme for calcium-48. Of course, it has a 0+ ground state, as all even nuclei had, but they have a very, very low 0+ state. And that tells me that there is some nuclear structure physics that is well beyond what we have done with DFT that we have to understand better. 0+ states are normally at very high energies for doubly magic nuclei, like lead, for example, that gives rise to the giant monopole resonance. So this 0+ state is giving me pause, even more pause, to suggest that calcium-48 is going to be a nucleus that bulk is going to be good. But again, just to conclude the very long-winded explanation, I think what you said at the beginning is correct. And hopefully we will learn about these beyond mean field correlations from coupled cluster. So thanks for the question, Bill.
Any other questions, comments?
Oops.
Okay, I have a question.
I had a question. Oh, sorry.
No, please go ahead. Please go ahead.
Yeah, in this graph you show with the radius versus the mass, there was this causality limit of how big or how small the radius can be. What is that actually? Where is it coming from?
Here?
Yeah.
Yeah, so causality limit normally means that you have a star that is so compact that essentially you will start violating the speed of light limit. So that's
okay.
all of that it means. So basically you want to stay away from that region.
Mm. And is there also a lower limit for the neutron star? Because it looks like all those masses go only.
That's a very, very interesting question that we do not know the answer. So of course, you want to know how big a neutron star, how massive a neutron star can be. You also want to know how small it can be, and that we don't have very precise limits. There are biases, right? If all that you can make is a neutron stars via core collapse supernova, is there a limit just inherent to the process? But in all honesty, I don't know the answer to that.
Okay, thanks.
Any other questions? So let me ask one. Particularly this slide where you are in right now. So when we had the first PRex result, it was something around 0.34 or something, right, for me, the result? Yes. So yeah. So then it decreased in PRex II. And do you think if it is measured again, maybe in MREX, it can go down further?
Okay, so you're telling me, so we have these 2 points, let's make it here. Actually, I do not know. I really don't know. Clearly within statistics, right? You're saying that within, and this is 1 sigma error bars, then you have a Gaussian around this point, right? So you decide if you want to come here, I mean, how much of that probability you include. So all I can say is that, first of all, I want to really express my gratitude to my experimental friends because this was a heroic effort. But of course, it's very easy for me as a theorist to say, yeah, you should lower the error bars by a factor of 2, but that requires an enormous amount of work. And as I said, at least in this regard, the parity violating effort at Jefferson Lab has been concluded. And the only option that we have is MESA wants to take the reins and then do the experiment. But MESA is a facility that they're building the whole at this point. So if it happens, and I have no idea when will it happen. So the other option is that we learn how to do hadronic reactions. Again, we have these 2 anchor points. And then when FRIB wants to measure the masses of the neutron skins of very exotic nuclei, at least you will have 2 anchors to say, okay, do I understand how to treat strong interactions in this context? But yeah, I don't know what the answer can be. But of course, you know, statistically, you can put as much weight as you want to get something much smaller.
Yeah, my question was from the other perspective, that how, as theoreticians, you can I mean attack this problem from the other side, that every time there is this new result, we are in discussion whether we should mitigate between some observation from the astrophysics and some observation from the laboratory. We need to reconcile them only according to the central values. We never talk about the whole range of them and then trying to mitigate in that direction. I was asking the question from that perspective. But
yeah, so I think from that point, I think we're making progress, right? I mean, essentially what we now have statistical tools to really incorporate not only the mean value of the result, but the entire error bar, and then obtain confidence intervals for all different quantities. And I think that many colleagues are starting to do that, right? So you input all the information that you have, you include even your prior biases, let's say through Bayesian estimation, and at the end you come with a posterior that, in my opinion, is well calibrated, that tells you soundly what are the values that you should be expecting.
So hypothetically, if it goes down, then what would we do?
If what goes down?
This MREX, if it measures it.
To tell you the truth, I mean, I would like to fight against nature, but I know I'm gonna lose. So if they go down, then we revise our prejudices. We try to understand what's going on. But to tell you the truth, I mean, even though I was a little bit taken aback by the CRex result, I think that's what communities need, right? You need a shock and say, yeah, so I thought I understood, but apparently I don't. So now we have more work ahead of us.
Can I make a comment about the comparison between nuclear physics experiments and astrophysics experiments? If you talk about radii, or you're talking about deformability, you're really talking about properties of the neutron matter equation state. And if that were the only thing that was necessary to describe neutron stars, that would be enough. But in fact, if you want to describe the internal composition of neutron stars, and as you go from different phases to other phases, the question of the symmetry energy becomes rather important. So I think that neutron stars observables, to the extent they're only sensitive to the neutron equation of state, will not be able to answer these questions. So I think that nuclear physics measurements are important, and the error bars are all big, even in the neutron star measurements have big error bars.
Yeah,
so,
I mean, I completely agree with you, Bill, and that's why I like to build this density ladder, because it certainly shows that every field has a role to play. But I think that some neutron star observables are certainly sensitive to certain parts of the equation of state, right? So I would completely say that if you want to understand masses, then of course that comes from very high densities, and maybe it's hard from any other field to make contribution. But I think stellar radii are in a very sweet spot. I think even heavy ion collisions that you and Betty and others do, I think that is a region that we can have some kind of overlap between stellar radii and heavy ion observables, because that's the sweet, I call it a very sweet region between 2 and 3 times neutron matter saturation density.
And I think these sort of, if I make one more comment, I think these sort of oscillations of interpretation are the nature of discovery science. That you will have results, and then the results will have error bars, and theory also has error bars. So the fact that things are changing, I think, is not surprising in terms of our view of it.
Yeah.
Okay, there is one more question. Raise hand, rather, from
Professor Viñas, it's a pleasure to listen to you.
The same to you, the same to you.
Thank you.
It's a pleasure, Jorge. Excuse me, one question related with, there is this other technique of dipole polarizability, at least for getting information about the equation of state. Can you say some words about this? Or?
Of course. And I didn't know you were going to be here, but I think I might have a slide. So here I have the polarizability, right? And of course you can have the normal giant isovector giant dipole resonance, but then also you have the PDR. Let me see. So one of the things that I've tried to do is when the PRex II result came out, I tried to see if we can reconcile the PRex II measurement with previous measurements of the dipole polarizability. And basically the conclusion was that the equation of state that PRex is suggesting is making the dipole polarizability to become much larger than what it was measured. So one of my conclusions is that there is certainly confusion there, because at that point I couldn't reconcile the relatively soft equation of state suggested by the electric dipole polarizability with the much stiffer equation of state that was suggested by PRex.
Okay, thank you very much, Jorge.
You're welcome.
Okay, there is another question or raised hand from Zidulin. Go ahead.
Hello, Jorge.
Hello, Zidu.
Yeah, it's good to see you again, and thank you so much for this very nice talk. So my question is that I don't know if I correctly get your idea. So did you say that the measurement of the calcium-48 neutron scheme is kind of model dependent?
So let me see if I understand. What you're saying is that is the measurement model dependent? Is that the question?
Yeah, but so somehow, I mean, I didn't right. So because I mean, from your discussion with the discussion a moment ago, it seems that some interpretation of that calcium-48 measurement is kind of model dependent.
Now I understand your question. Yeah. Well, I think that from the point of view of nuclear physics, there will always be some kind of model dependencies. Now, the question is, if you want to extract bulk properties of infinite matter, then of course you want to minimize, let's say, nuclear structure effects, right? You want to have a relatively simple nucleus that will illuminate what are these parameters of the equation of state that you want to determine. So in that regard, lead is a very benign nucleus. So back to your question, I think that what happens with calcium-48 is my fear is that there are correlations that are beyond what you have in your density functional theory that essentially preclude you from making very strong conclusions just from, let's say, mean field arguments. And I think that one of the things that I try to point out is, first of all, this very low energy 0+ state, which is very, very hard to understand from the perspective of a mean field. And also the fact that ab initio coupled cluster calculations seem to be able to reproduce a thin scheme. So my guess is that every model has model dependencies, but in the case of calcium-48, there is even physics that goes beyond some of these mean field or density functional theory framework.
Okay, yeah, thank you so much, Jorge. So yeah, now I understand more. So actually, I'm asking this question is because that, yeah, if you remember, I mean, previously, maybe people are discussing if we can measure the full weak charge.
Correct.
Full weak charge, this density distribution of the calcium-48. By doing that, maybe we can remove all the density model dependency of the kind of the measurement. And I'm thinking probably this might be the one way having a more precise understanding of this neutron spin of the calcium-48, and probably it can somehow reduce the tension between the calcium-48 and the lead-208. I'm not sure, but this is what I just imagine, yeah.
Okay.
Yeah, thanks so much.
Yeah, thank you.
Okay, we have another raised hand by Tianqi Xiao. Please go ahead.
Hi, George. I'm following the last question. And since there is some kind of problem with the calcium-48, are you still pretty sure about the systematics for PRex? So are you still sure that PRex has little systematics due to your assumption of energy density functional? Are you still sure about it?
Is this a theoretical or experimental question?
So experimental side, there's like a Coulomb distortion calculation. That part, are you sure? And in a theory point of view, the density functional side, are you sure about the systematics?
I mean,
that's my question.
Yeah. Well, yeah. So some of the, I mean, so let me just point out two things. Of course, you can never be sure, but I'm very confident that in the context of density functional theory, or if you just want to say mean field theory, I think lead-208 is a more closer approximation that calcium-48. I mean, I think that there are several things in calcium-48 that are difficult to explain. I mean, you probably remember charge radii as you go from calcium-40 to calcium-48 and even beyond. One of the things that is always been very hard to reproduce with mean field theories is the fact that the charge radius of calcium-40 and calcium-48 are the same. So that is hard. This 0+ state will be very hard. So I guess the only thing that I'm telling you is that there are some things that happen in calcium-48 that do not happen in lead. But if you want a statement from me, if I'm completely sure that there are no systematics, then of course I cannot be completely sure. But I think that the picture that we obtained with LED 208 by calculating different observables certainly tends to believe that the description that we're using for LED seems to be adequate. And I apologize if I cannot be, if I cannot answer the question.
Yeah, okay, that's very okay. Thank you.
You're welcome.
Okay, we had a really fruitful discussion after the talk, the wonderful talk you gave.
Thank you so much.
So, thank you very much.
It's my pleasure.
We ask anybody who is interested to join the Gather Town, the link I just posted in the chat box. So if there is no other questions, we thank Jorge again. And have a nice